Hey guys, this morning I'd like to talk to you a little bit about how much energy there is in spring. Well, let me clarify. Not the season of spring. How much energy there is stored in a bed spring or a rubber band or something that's either stretched or compressed. The formula for that's relatively simple. It's 1 half kx squared. And a reminder of what k and x is. K is the spring constant. That would be measured in some sort of force divided by distance units. And for our calculations to work out into Newton meters, that will have to be in newtons per meter. And x is the distance that the spring has been stretched or compressed. That's the change in length from what it naturally is. Again, for that to work out into Newton meters, x will have to be in meters. And I want to remind you the original force formula that I gave you for springs was F equals kx. And so this is just a little variation on that. In fact, for you calc students, I want you to notice that this is the integral of force. And that's fairly common that energy tends to be the integral of things. So a little more about what a spring coefficient is. A spring coefficient is a number that's unique for each spring. Unfortunately, you usually can't just look it up on the package or something like that. You usually have to either be told it or measure a couple different tensions, have the spring hold a couple different weights and measure how long it is. If you plot that on a scatter plot, then the slope of the force versus length graph would be your K value. And so, as an example, I wanted to go back to a fun video game that I enjoyed playing growing up, just the simple Windows pinball game, and thought, let's figure out how much energy there was stored in the spring down at the bottom. When we pull that plunger back and let go, then that energy goes into the ball and moves it. So if we can figure out how much energy there is stored in that spring, then we should be able to assume that all that energy goes into the ball and figure out how fast it goes too. So let's look at how much energy there is stored in the ball. So potential energy of a spring is 1 half times k times x squared. And for us, that would be 1 half. And k is 24 newtons per centimeter. 24 newtons per centimeter is, if you multiply that by 100, 24 newtons, or 2400 newtons per meter. And if we multiply that by the distance that we pull it back, it said 10 centimeters. So 10 centimeters in meters would be 0.1 meters. And that would be squared. And if we multiply all those things together, 0.5 times 2400 times 0.1 squared, we got, oops, hit the wrong button, sorry guys, equals 0.5 times 2400 times 0.1 times 0.1. We get about 12 Newton meters, or 12 joules. So there's 12 joules of energy stored in that spring when we pull it back. Now let's see how fast that ball is going, and to do that, we'll have to calculate or assume that all the potential energy that was stored in that spring gets converted into the kinetic energy of the ball, and it's not entirely true. Some of that energy is going to turn into to sound, and some of it turns into heat because there's some friction involved and all that sort of stuff. But let's assume that everything goes into that. And if we remember, we've got 12 joules is how much is stored in the spring. And the kinetic energy of the ball is, the formula for that is 1 half times the mass of the ball times the velocity squared. And so we need the mass of the ball, and well, they didn't give us the mass. They told us the density, and they told us it's well, it's a ball, so it's spherical with a radius of 1.5. So we'll have to put this equation aside for a second and look at how can we calculate the mass of the ball. So the density is told to us, and the density formula is that that's mass over volume. And so if we multiply both sides by volume, we get that mass is the same thing as density times volume. And our volume is a sphere, and so if we look up the density formula, or the volume formula for a sphere, that is, let's see, put a row in here, and volume for a sphere is 4/3 pi r cubed. And so let's plug in some numbers. I think we've got what we need. The density is 4, and that would be in grams per cubic centimeter. Oops. And I'm going to want my mass to come out in kilograms, so let me add a conversion factor second. There's 1,000, let's see, there's 1 kilogram in 1,000 grams. So that's kilograms per cubic centimeter. And now let's find the volume of that pinball in cubic centimeters. So that would be 4/3, and we need a pi, and we need the radius, which is 1.5. So 1.5 centimeters, and that is cubed. So let's calculate that a moment. 4 divided by 1,000 times 4 times pi times 1.5 raised to the 3rd power divided by 3. We get a mass of about 0.0565 kilograms. There we go. So now we ought to be able to use our equation over here, since we know, oops, not that one. Here's the one we were working on that had a mass in it. So let's rewrite that. We've got 1/2 times the mass was 0.0565 kilograms times v squared. And so to solve this, I'll take 12 joules and multiply it by 2 to get rid of the 1/2, and divide by 0.0565, and that'll give us v squared. And so if we take the square root of that, that should give us v. And quickly calculate that. So equals a square root of 12 times 2 divided by 0.0565, and we get about 20.6. And so 20.6, this would be the standard unit for velocity would be in meters per second. And so 20.6 meters per second, roughly 40 miles per hour. I think that seems fairly reasonable for a pinball. So anyhow, there's an example of using spring energy, how much energy there is stored in a spring, to calculate how fast something goes and so forth. So thanks for watching, and I'll catch you next time.